In the previous lecture we started the topic of kinetics, and as we discussed, the kinetics involve calculation of forces which are creating the acceleration. We also discussed the equation of motion and the Newton's second law, the validity of the Newton's second law for various cases. Then we also discussed the definition of inertial frame of reference, then equation of motion for a single particle and the system of particles. So this is the summary of the topic of development of the equation of motion. So we can go through the points. So the equation of motion F equal to ma is based on experimental evidence. There is no derivation for the equation of motion, and it is only applied when the frame of reference is the inertial frame of reference. And the inertial frame of reference is the frame of reference which does not rotate. It translates with constant velocity, or it is at rest. According to equation of motion, the unbalanced force will result in acceleration. If the forces are balancing, all the forces are cancelled out, then there is no acceleration. So F equal to ma is valid in the inertial frame of reference. If the frame of reference has some acceleration, then the equation F equal to ma will not balance. Then also the mass, we are familiar with the definition of mass, but in dynamics it is the quantitative measure of the resistance to a change in velocity. So it is an absolute quantity, it is not affected by location. Then weight is a force, it is caused by the earth gravitation, and it is not absolute. In comparison to mass, it is not absolute, it depends on the altitude. It depends on the altitude from the earth's surface. Now, similar to the topic of kinematics, there are various methods of analysis. In the previous topic we explained there are three systems usually which are used for the engineering problems. One is rectangular coordinate system, second one is normal and tangent, and the third one is cylindrical coordinate system. So we start with the rectangular coordinate system. In the rectangular coordinate system, any vector is written in three components in general. There are x, y, z axis, and the corresponding unit vectors are I, j, k. So if the force is acting on a particle in general, it will have three components: fx, fy, and fz. Similarly, acceleration is a vector. It will have three components: ax, ay, and az. So we can see the sketch. The three coordinates are shown, and suppose this blue one is the path of the particle, and this is the instantaneous location of the particle at any time. So the resultant force or the complete force is shown in three components: fx, fy, and fz. This is the vector equation summation F equal to ma. In the nomenclature of book, as we have described before, the bold symbol is for a vector. So this is the vector equation summation F bold equal to m multiplied by a bold. We will write the components of force Fx, Fy, and Fz. There can be multiple forces in F. x, y and z direction, so we are including a summation sign. Then as a result of these forces there will be acceleration. The acceleration will have three components: ai, ax, ay and az. Now to have the balance equation, the unit vector I should be same on both sides, the coefficient should be same. The corresponding component equations, this one is the vector equation, the corresponding component equation is summation fx equal to max, similarly summation fy equal to may, and similarly for z direction summation fz equal to maz. So we will be using these three basic equations when we solve the problem in a rectangular coordinate system. It depends on the given data. It depends on the given data and the required output that which coordinate system has to be used. Sometimes the data is such that it is easier to solve in rectangular components, and sometimes the data is such that the normal and tangent coordinate system is more convenient. Similarly, sometimes the information provided in the problem is such that cylindrical coordinate system is easier. Now we consider the equation of motion in tangent and normal direction. Now suppose the particle is moving in the curved path and the curved path is known. The equation of motion can be written in the tangent, normal and binormal directions. The motion takes place in tangent and normal direction, but the corresponding three directions are tangent, normal and binormal. Similar to the rectangular coordinate system in which there are x, y and z, in the tangent and normal direction the corresponding directions are tangent, normal and binormal. In the topic of kinematics we only consider the tangent and normal direction because the motion is described with the help of tangent and normal only. There is no velocity component in binormal direction. Similarly, there is no acceleration component in binormal direction. The motion is only described with the help of tangent and normal. But when we come to kinetics, there can be forces in the binormal direction, but the forces are balanced out and there is no acceleration in the binormal direction. So again we consider the basic equation of motion summation f equal to ma, and then we write the components summation ft, summation fn and summation fb. The corresponding unit vectors are ut, un and ub. Acceleration will have two components, at and an. Because there is no motion in binormal direction, so there will be no term for the binormal direction for the kinematic parameters. When we compare the two equations, we get the three component equations: summation ft equal to mat, summation fn equal to man and summation fb equal to 0. You can see the schematic. This is the path of the particle shown with the help of blue line, and this is the instantaneous position. So when we draw a tangent, we get a tangent direction, and perpendicular to this towards the center of curvature, we have the normal directions. Normal and tangent are perpendicular to each other. and there is another axis which is perpendicular to both tangent and normal. This is the binormal direction. So motion is described with the help of tangent and normal, but there are three forces, there are three coordinate axes which have angle of 90 degree. This is the case where we can apply the tangent and normal components. Suppose there is some object moving on this curved path and we are interested in finding the forces and acceleration at this particular location, then we can use the tangent and normal direction. Normal direction, and this one is the tangent direction. Perpendicular to both will be the binormal direction. From the previous topic, we know that at is tangential acceleration and it is equal to dv over dt. It represents the time rate of change in the magnitude of the velocity. Acceleration occurs due to change in velocity. The velocity magnitude can change and direction of velocity can change. The change in magnitude of velocity leads to tangential acceleration, and change in direction of velocity leads to normal acceleration. When there is tangential acceleration, there is some force in the tangential direction to change the velocity magnitude. Similarly, when there is normal acceleration due to change in direction of velocity, there must be some force in the normal direction to change the direction of velocity. Now we do two problems related to the topics which we have covered. One is relative motion, which was in the previous lecture. As was discussed in that topic, that sometimes we are interested in the relative kinematic parameters, that is the relative position, relative velocity and relative acceleration in comparison to the absolute position, absolute velocity and acceleration. In this problem, there is a car traveling BA. There is a car traveling A in the horizontal direction towards left, and there is another car which is moving in a curved path. The velocities are given. Velocity of A is 55 miles per hour, velocity of B is 40 miles per hour, and at the instant shown, the angle between direction of A and B is 30 degree. Another information provided in the problem is that B is increasing its speed by 1200 mile per hour square, whereas the car A is maintaining its constant speed. Now we have to find the velocity and acceleration of B with respect to A, and car B is moving along a curve which has a radius of curvature of 0.5 miles. The absolute direction of B is towards left, that is towards west and south, and it is moving along a curved path with a certain velocity of 40 miles per hour. But from the point of view or from the respect of A, the direction of velocity can be different. The velocity shown is in the absolute direction. In absolute direction is towards left and upward, that is southwest, but from the point of view, from respect of A, it can be different. So we use the basic equations which we develop for the relative coordinate system. We write the components of velocity of B. At the instant shown, the angle is 30 degree. So velocity of B will be minus 40 multiplied by cos 30, and this will give the x component. Then for the y component, 40 multiplied by sin 30j. After simplification, we get minus 34.6 plus 20j. Velocity of A is towards left, so it is minus 55i. To determine the relative velocity of B with respect to A, we have VB minus VA. So we subtract the two velocities, VB minus VA. VB, this is VB minus VA, is equal to 20.4 I plus 20j. If you want to find the magnitude, we take the squares and then under root, we will get the velocity magnitude. So velocity magnitude is 28.5 miles per hour. Now this is the velocity of B with respect to A. Velocity of B is 40 miles per hour, but from respect of A, the velocity will be less. It will be 28.5, because both are moving in the same direction, not exactly in the same direction, but both are moving towards towards west. Both are moving towards west. Then from point of view of A, the velocity of B will be less than 40. It is 28.5. This is same as the concept of the simple cases. If the two particles are moving in the same direction, then, or two objects are moving in the same direction, then from point of view of one object, the velocity of the other object is relatively less than the absolute velocity. But if the direction of the two objects are different, then from respect of one object, the other object moves with a greater speed than the absolute speed. So similar is the case over here. The velocity of B is less than the absolute velocity from point of view of A. Now we are interested also in determining the direction of the velocity. So direction of velocity is y component divided by x component. This gives 44.5. In the actual case, in the absolute case, B is moving towards left, and it is moving at an angle of 30 degree with respect to horizontal, and that 30 degree is towards left and in the west direction. But from an observer point of view, which is attached with A, here we have the moving coordinate system attached with A, and we are determining the velocity of B with respect to A. From point of view of A, the car B is moving at an angle of 44.5. That is, from point of view of A, car B is moving towards right. It is moving in the east and north direction. So there is significant difference if we see the direction in the direction from the absolute sense and from the point of view of A. Actual direction is towards left, but from point of view of A, it is moving towards right. Now we come to the calculation of acceleration. It is mentioned in the problem that particle A is moving with a constant speed. When particle A or car A is moving with a constant speed, then the tangential acceleration is 0. Since car A is also moving in a horizontal path, it is not changing its direction, the normal acceleration of A will also be 0. So there is no acceleration of car A. There is no change in magnitude, there is no change in direction. In case of B, the car B is moving on a curved path, so there is some normal acceleration. The direction is changing. Similarly, it is increasing speed. It is increasing speed at a rate of 1200 miles per hour square. So it will also have the tangential acceleration. So we have to find both acceleration. Normal acceleration is Vb square over rho. The radius of curvature, it is given 0.5, and velocity of v is 40. So we determine, we calculate, and we get 3200. The speed is increasing at a rate of 1200 miles per hour. So tangential acceleration is 1200. There is no acceleration of car A. The relative acceleration of B with respect to A or absolute acceleration of B, both are same. Since there is no acceleration of car A, the relative acceleration of B with respect to A or absolute acceleration of B, both are same. We can see the various directions. Tangent direction is 30 degree at the instant shown. Normal is towards this direction. It is at 60 degree with the horizontal. This is x direction, this is y direction. We can write the components of acceleration in normal and tangential direction, and we can write in terms of x and y. So 3200 multiplied by cos 60. 3200 is normal acceleration multiplied by cos 60 will give the x component of, will give the acceleration x component due to normal acceleration. Then subtracted by minus 1200 cos 30. The tangential acceleration is 1200. We take the component, we multiply with cos 30. The cos 30 will give the acceleration in x direction, and since it is towards left, there is a negative sign. Then we find the y component of acceleration. For y component of acceleration, 3200 is the normal acceleration, and to find the y direction we multiply with sine 60. Similarly, we obtain the y component of acceleration due to tangential acceleration. So tangential acceleration is 1200 and we multiply with sine 30. So after solving, we get 560.8 I plus 3371.3 J. So this is acceleration of B in terms of rectangular components. Then we find the magnitude of acceleration of B with respect to A, or we find the magnitude of acceleration of B. Both are same because there is no acceleration of A. We take squares and then under root we have 3418 mile per hour square. Then we find the direction of acceleration. Direction of acceleration is 80.5. It is obtained by dividing the two components of acceleration in y and x. We get 80.5. So direction of acceleration is 80.5. That is, acceleration is occurring at an angle of 80.5 measured with the horizontal. It is somewhere here. And what does it mean? From the point of view of A, the car A is moving in the horizontal direction towards left. From point of view of A, B is increasing its speed in this direction. The actual direction of B is towards here. The relative direction from A is 44.5, somewhere here. But since there is change in magnitude of acceleration and direction of acceleration, the acceleration of B is in this direction. We can also solve the same problem, or we can obtain the direction of acceleration and we can obtain the magnitude of acceleration using the normal and tangent components. Suppose we obtain normal acceleration 3200 and tangential acceleration as 1200. We can determine the magnitude in the similar manner. We get 3417. So it is same as over here. This means either we can solve, we can convert the normal and tangent acceleration in terms of x and y, or we can directly determine the magnitude of acceleration of B with respect to A using the magnitudes of normal and tangential acceleration. Similarly, we can determine the direction. The components are 3200 and 1200. So suppose we determine the angle using normal and tangent. We get 69.44. So this 69.44 will be measured with respect to normal and tangent. So 69.4 will be between tangent and y. There is angle of 60, and after this 60 we take 9 more because it is 69. It is 69.4. So we take 60 and plus this 9, because this 69.4 is measured from tangent towards the normal. So towards the normal it is 69, so it is somewhere here. So if we determine the direction from x, it will be around it will be same as it is determined from the x and y coordinate system. It is about 80.5, so it gives the same result. So we can use both methods, tangent and normal, or we can use x and y. The basic reason for solving in x and y as I did in this problem is that we determine the velocities using x and y or I and j, that is the rectangular components. So for that reason the acceleration was obtained in terms of rectangular components, but we can determine the acceleration using the normal and tangent component as well.